Thank you very much, Short, for the introduction, and thanks a lot to the organizers for inviting me for this follow-up workshop. What I will be talking about is some combination of work with Dominic from his PhD student, and some new work with him and my current PhD student, Julia. But let's start with the work with Dominic. That is the starting point, and we got started about this some years ago when we were thinking about low rank recovery problem. One of the problem that we were interested in was blind deconvolution. You probably, when you think about blind deconvolution, you may think about something like this. So you have the blur as the motivating application. So you have some image, and then in the process of capturing it, there's some blur which is represented by a convolution. So you're having a convolution of some blur kernel and some image, and then this is the observation. And what you would like is to get the image back from this representation. So in this talk here, I will use a simplification that is mathematically things a little nicer, and that is I'm considering circular convolution, because the problem with considering the convolution of these two images is that they don't exactly that the convolution will have a different size than the two images, so that you will have to do some amount of zero padding or something. So we will assume that is all incorporated in the signals already. So that's why we're doing a circular convolution of two signals of the same length of L that will also result in a signal of length L. And this is not the main motivation that we will have here, because of some things that you will see. Maybe we are looking at this motivated by a problem in wireless communication, and that's as follows. So you have a message that you want to send from some device to an antenna or a receiver, and what happens is that it goes the direct path, but it also goes a little bit longer paths. So it's going to these houses and it's reflected. And if you want to make it sort of more accurate, you would also incorporate some approximation of Doppler shifts. We don't getting some time frequency representations. We're not doing that here. So we're assuming that what we're getting at the antenna is a superposition of different delayed signals, so different shifts of the signals, and that gives us exactly this convolution. So why, I mean, it's the same model, it's the same convolution. Why are we interested more in this application? The reason is that we have different degrees of freedom here. Namely, we are actively sending the signal through the channel. So we have the possibility to do some pre-processing to the channel before sending it. And then also we have some way to model the channel. Here we are using the simplest model for both these the channel and the signal. Namely, we are assuming that the encoding that we're doing is just linear, in the sense that we are embedding our signal into a higher dimensional space with a known embedding matrix C that we are to design. And then the channel model is also a linear model. So you could think, for example, that you say only here we have a lot of paths where the signal could potentially go, but we are only assuming that the first few of them are active. So the shortest paths, which would correspond to a matrix B that could be, for example, something like the first few columns of the identity matrix. So the important thing is C, we have some potential to design. B is given to us by the model. And in the case as before, we have this convolution of these two things, and we want to recover our message M from this convolution. The starting point, that was a number of years ago when people started looking at this problem with the machinery of low-rank matrix recovery. And at the time, what a lot of people did, and what was always a very natural approach, was lifting. So they were saying, okay, we observe that this is a bilinear map here in the inputs H and M, and a bilinear map is a linear map in the outer product of H and M. So we are having the problem of reconstructing this rank 1 matrix HM star from some linear measurements that are structured. And so this looks already very much closer to the low rank matrix recovery problems that you may be used to. And so that's why it has also been studied in this context of the literature. So here we're getting a low rank matrix recovery problem. We want to get a solution of this equation here that is also of, in this case, rank 1, low rank in general. So of course, the natural, I mean, I think this is a more a recap to most of you. The natural way is let's try to minimize the rank of this problem, of the solution. That is something, I mean, you've also heard the talk by Christian, who mentioned this earlier yesterday. So this is, of course, not an appropriate way to do it. You have to use some amount of relaxation. And what was proposed in this paper here by Ahmed, Recht, and Romberg was to do a convex relaxation using the nuclear norm. And the nuclear norm is just the sum of all the singular values. In some sense, it's the rank analog to the L1 norm when you're thinking about sparsity, because if you think the matrix has low rank, then it means just if you look at the vector of singular values, that is sparse. So then you're taking the L1 norm of the vector of singular values, and then it's exactly this nuclear norm, what you're getting. So I think this may not be new to many of you. And here, just let's go back to this problem and try to get these things together. And so what, let's recall, this was our model assumption, BH convolution with CM. And then we have some noise. And in this talk, I will be particularly interested in adversarial noise. I know that there's also papers studying different random noise models, but on the one hand, it's just of interest to how adversarial perturbations compare to random perturbations. And on the other hand, I mean, I talked to some people in statistics, when they talk about problems like covariance estimation, it's just very difficult to fit. Like they have some noise model that's somewhat random, but it's so involved because it comes from these structures that they have that it's just not easy to fit it in one of these categories that are typically employed there. So that's why if we have an idea of what happens, just knowing that the norm of the perturbation is small, that is certainly something that would be of interest also for those applications. So now let's recall what we had here. The matrix C is we have the design. We have the possibility to design it any way we like, because this is something that we actively apply before sending the message here. We are just choosing it at random, so using Gaussian entries. And for the other matrix, one example that I gave you that could be motivated was just looking at the first few columns of the identity matrix. In any case, we're having it a little bit more general here. This is satisfied, so we want it to be a tight frame, so that B star B is the identity. And also, if you're looking at the Fourier transform of this has rows of equal norms. So that's just to prevent that there are some entries in the submitted signal that have no significance or something like this. So we want things to be equally spread. If we don't have this, it's more technical. Probably you can still do it, but this is satisfied for the example that I gave you, and just makes the analysis a little simpler. So, and under these assumptions, this was the assumptions of this paper by Ahmed, Recht, and Romberg. They showed that with the number of measurements that is more or less linear in this dimension L, that's you have to think about the number of measurements is a little bit more implicit here, because you are taking two vectors of length L and looking at the convolution. So the resulting vector has L entries, but so L should really play the role of the number of measurements, and then the dimensions of the underlying vectors. Let's go back here. So what the H and the M that you put in, that you're embedding into the higher dimensional spaces, these are playing the roles of the degrees of freedom, and they are called K and N here. And then what they show is indeed with high probability, the minimizer of the semi-definite program satisfies in a condition like this, which is very good, because you think of if eta is the noise level. So if the noise level is 0, that means the reconstruction error is 0. So you're getting an accurate reconstruction if you have no noise. So the coherence parameter, I will say something in a second, And this is already okay. What I already said, for no noise, we have exact recovery with a near optimal number of measurements. But at the same time, what is a little puzzling, or what was a little puzzling to us looking at these results here, is this factor square root of k plus n. Because this is not what you see when you run experiments with sort of certain random inputs. And it's also not something that you have in the results for the sort of less structured scenarios like Gaussian measurements of rank 1 matrix or something, where you could use RIP-based techniques or something like this. So that's why this was the starting point. We thought, okay, maybe this is a proof artifact, then we can think about how to get a better scaling in the noise level. So before I go into more details about this, let me just quickly talk about this coherence term that we're having. There is basically consisting of two terms. There's the mu1 term and the mu2 term. The mu1 term is something that is sort of considered to be necessary in some sense. So we are taking the signal, we are looking at the sort of BH is this thing that we're putting into the convolution, and then we're looking at the Fourier transform and asking that the infinity norm is somewhat controlled. Why is this something that we think that is natural to assume? Because what happens if it's not controlled, so that we have large entries, that could be that the mass is concentrated in just very few entries. And that means, on the other hand, that other entries or a number of other entries could potentially be small. And if we're thinking about it, a convolution is nothing but a pointwise multiplication in the Fourier domain. So if one of the vectors is has entries that are very small, also the information contained in the other vectors in those particular entries is getting lost. So that if that happens for a number of entries, that's bad. And basically information can get lost and cannot be recovered. And this is why we want to prevent this using this condition. And indeed, in this paper that I cited by Ahmed and co-authors, they did numerical experiments and showed that indeed, if this mu1 constant here is large, there are more measurements are needed. On the other hand, the mu2 constants is a technical term, and some part of the result that I'm not talking about today in this older paper, we also showed that in a certain circumstances is not needed, but I will not go much into this, and because it's just technical to explain. So let's just quickly recap, how did they prove this result? So the idea of the paper and a number of results in matrix completion and other papers was based on a so-called dual certificate. So the idea is, and this is now I'm talking a dual certificate. This is a concept that's very common in the analysis of optimization algorithms or convex optimization. So you are looking for some vector, or you can also, if you either look for this or for this, you can also say you're looking for this vector y in the range of the adjoint of the linear operator, such that when you're projecting it onto Tx naught here, I should have put it on this slide, it's the tangent space to the manifold of, in this case, rank 1 matrices at the position x naught. So you're projecting to the tangent space of the rank 1 manifold, and then you're getting sort of the true solution. And if you're projecting to the orthogonal complement of this tangent space, you're getting a constant that's less than 1. And it's I think that's something that's well known. If there's such a dual certificate, this and you have this minimization problem with the nuclear norm with equality constraint that I showed you earlier, we get the true solution back. So, and how the proofs proceeded also in this paper and in others is that they say, okay, maybe it's difficult to find an exact dual certificate because we have this equality condition here, and they want David's idea was to use a random construction. So with a random construction, it's very difficult to satisfy an equality constraint. And so that's why he said that maybe it's enough to have, under certain conditions, to just have an approximate dual certificate here. When we revisited in the context of a book chapter that we wrote for this book by this priority program that Holger coordinated, we just saw, okay, just try to look more into how to find an exact dual certificate, because we know that exact dual certificates are closely related to there's the solution. So if there's an approximate dual certificate, then that, and it was shown that under certain circumstances, this implies that there's an exact solution, then there should also be an exact dual certificate. And indeed, we can quantify this here and say that if on this tangent space to the rank 1 manifold, which we have the restricted isometry property with our map, which is something that is satisfied for these maps that we're looking in this talk here, then in fact we can find an exact certificate, and we can quantify this constant c that is supposed to be less than 1 in terms of this restricted isometry property constant delta. So this is something that at the time when we wrote this book chapter, it was just a nice observation to formulate it like nothing new really. But here in what I will show you later, we will use this exact dual certificate for the proof. So that's why I stated it here. It's sort of important for us to have. But of course, this is at the end. So let's go back to ask what about these dimension factors. Are these dimension factors necessary? Let me go back and recall what dimension factors I'm talking about. So what we expect and would like if we put error on this size of eta onto our measurements, then we would also have expect and hope for a reconstruction guarantees on the order of eta, which is what we have in many cases. The normalization is such that we should expect this, but this result here doesn't give it to us. And so indeed, we were very surprised when we found that this is not the case. So in fact, what we found is we found a matrix that is admissible in the sense defined in this previous paper, that such that with high probability, so that there is a tau naught such for all tau less than tau naught. This is sort of the threshold that you are looking at. So we want the small perturbation that is not satisfying these constraints. And so let's think about what if we are asking, is the reconstruction error of order eta? And in order to say no, it's not, then what do we need to prove? We need to find an alternative solution that is not satisfying this constraint. What does this need to satisfy? First of all, the alternative solution, the bad solution, so to speak, needs to be feasible. Because if it doesn't satisfy this feasibility constraint here, there's no way that the nuclear norm minimization problem would find it. So this is checked. The second, of course, we're doing nuclear norm minimization. So this solution wouldn't cause a problem for us if it didn't have a nuclear norm that is smaller than the true nuclear. So this is also what we have. But then here we know that what we would like to show is that the reconstruction error is on the order of this tau that we're having here as our approximation error. So on the measurements. So if we want to get a counterexample, what we need is that it's not less or equal to tau, but larger or equal to tau times some dimensional constant. And this is exactly what this result is establishing. So indeed, we can show that it cannot be true that any solution that has a smaller nuclear norm than the truth is actually close to the true solution. So this dimensional factor looks a little bit different than what we had before. Let's just try to put it into perspective. And in order to see what we get, let's just assume that we are in the competitive regime. First of all, we had two different dimensions, one for the input signal and one for the parameter vector. Let's assume they're the same. And then also what we are hoping for is a number of measurements that scales. This is sort of the degree of freedom and up to logarithmic factors somehow, scales, the number of measurements scale like this. So if L is then the constant times k up to log factors, we're plugging things in here, and we're getting square root of k plus n, exactly what we had in the result. So the factor square root of k plus n is not a pure proof artifact. So this needs to be there in some sense, but at the same time, I should say we have to be cautious, because what we have said is that there is an alternative solution that there is preferred to the true solution in terms of the nuclear norm. There could still be a third solution that's again close to the true solution that has an even smaller nuclear norm. So this is something that is open. So we don't know this, but in any case, even if that would be the case, this would show that the problem is somewhat unstable at the true solution point, and so then even that may, in that case, it would not be optimal, or you wouldn't want it. So let's quickly go into how we establish this. So let me recall one way how to estimate and analyze low rank recovery problems is using so-called descent cones. And here I apologize like this. The best way to visualize a descent cone is if you're thinking about the sparse recovery problem, because you have a pretty good idea, visual idea how the L1 ball looks like. That would be the convex relaxation of the sparse regularization, where as for the nuclear norm ball, in order to have a meaningful image, you need at least 4 dimensions, and that's a little bit more difficult to visualize. So let's look at this problem, but with caution. We will say later why we have to be cautious, but to get the idea of how these things are established. So if we had the L1 ball, then the idea is that at this tip here, where we're meeting this is the space of the true solutions, and this green thing is the set of all the points that have a smaller, in this case, L1 norm than this point here. In the case that we are interested in would be the nuclear norm. And then we are locally approximating this here next to the corner by a cone. In this case, that would be this object here. And so we're estimating, in the end, if we want to have a unique solution, we just need to show that this cone intersects this space only in this one point x naught. So this is the cone of all directions, such that if you allow for a small perturbation epsilon, the nuclear norm will not increase. So, and then if you want to make it quantitative with noise, that's what we are after, then we have to also use a quantitative estimate, and that's the conic singular value. So this is defined like this. So we are asking, what we want is, now we are allowing for a small perturbation, and we're asking, so what's the quotient of the perturbation that we add to the measurements and that we add to the signal? And this is the quantity that we're interested in the context of the previous setup. And indeed, this is also how the proofs work for, say, Gaussian measurements. You just estimate this conic singular value, you provide a lower bound and show that it scales, because this conic singular value here scales like a constant. So you have just a constant times the noise level eta as the reconstruction error. And here we already said, like here, this is independent of the anchor point. Like for Gaussian measurements, it doesn't matter at which point you are, you can estimate the cone always in the same way. And this is already something that we cannot expect here, because we know that if we have an incoherent case, it will behave much better than in the coherent case. So we cannot have an analysis that is agnostic to the anchor point. Yes?
But it will depend on the rank and so on.
Yes.
Yeah, I mean, it is. I mean,
okay. Yeah. Okay, I guess. Yeah. Let me cross this out. No, but yeah, okay. Even like I'm thinking of on any point on the rank manifold, like because we're always looking also at the tangent space, and then so we have to somehow assume that we're working on this manifold. But even on that manifold of all objects of the same rank, it will be very different in the case that we're considering here. And that's why it's also the idea that here we are looking at this, but we're showing that basically in the case that we're having here in the structured case, these conic singular values, they are actually quite small. Then like they have this dimension is constant in the inverse sense. So we're showing that they are not bounded by a constant. They don't behave like a constant. They're actually much smaller than a constant, and that's why how we prove this result. So, okay, this is a negative result in some sense, but so let's see, is this really the end of the story? And this is now where the very new work comes in that I would like to present you next, with just joined with my master student Julia and also with Dominic. And let's have a look more on why we can hope for more. So the descent cone is a local approximation to the descent set, right? This is what I showed you previously. I said you should exercise caution. We had the L1 ball, and it was very well approximated by the cone in a vicinity. So the geometric intuition here is that close to the kernel in the structured case we're considering here, the descent set is not as pointy as we had it before. So if we should think about it more like this red curve, this red shaded region, this here. So and now let's see, if we want to approximate this by a cone, the cone has to be very, very wide, because it's almost tangential here to the point. So we have to take a very wide cone. And the strategy that we did in this first paper where all these negative results are also cited, we said, okay, let's, if this is a bad region everywhere, it's close to tangential, close to the manifold, let's exclude this and let's just look at large noise levels. So basically everything that's outside of the strip. And then we can approximate things by the green cone. But at the same time, if you look at the set, okay, this is maybe an okay idea to do, but if it really looks like this, then maybe we should use it. We should just move away from the cones and not look at conic approximations anymore, but maybe something that looks more like a parabola. That would be a better approximation. And this is sort of the idea of what I will show you in the rest of this talk. This is the if you think about what would the parabola give us here. Basically, if you think of this as an exact parabola, then locally here, this would look like a square root of the noise, like the reconstruction error would scale like a square root of the noise level. And this is indeed what we have in our results here. So this is exactly the same number of measurements that we had before in the results of Ali Ahmed and others. And now we have here the square root of eta as the scaling that we get for the reconstruction. And this is, as I said, this is locally close to manifold. At some point, there's a maximum of this quantity and then something that's linear. So at some point, it would just we were just using the cone. Later on, it will not, for very large eta, it will not scale as bird anymore, but at least locally close to the cone, this is the approximation behavior that we found. And here I have sort of spelled this out just to make sure that to show that the scaling is correct, because if you think about here, the noise level is added to the measurements. So how can it happen to the square root? So that the point is really that we're getting the Frobenius norm of the matrix that sort of compensates for the difference in scaling factors that adds here. So if we normalize the Frobenius norm or do something like this here, then we really have something, the maximum of square root of t and 4 times square root of tau and tau. And so in some sense, this bridges the results for the small levels that I showed earlier, where the dimensional constants are not so bad, right? If the noise level is extremely small, then maybe we can deal with the dimensional constants. And the large noise levels that I just showed you the picture of, that's like looking everything outside of the strip, and this is somewhat in between. And there's no which I didn't mention is also these other results had some spurious log factors that showed out they are also not happening here. And so that's why this looks, I mean, we're very happy about this. So are there any questions with regards to the statement of the result and the general intuition? Okay. So then let me just give you a quick idea of how this is proved. So, because I think one idea is maybe something that could be useful otherwise. So the restricted isometry property, we just make some few check marks. Recalling, this slide is about recalling things that I've said earlier. On the one hand, we can assume that there's the restricted isometry property. This has been established for, like this is on this tangent cone, on the, yes, on the tangent set to the tangent plane to the rank 1 manifold at the right solution. So this is something, this is a low rank space where the restricted isometry property has been established by previous literature. And then now we're using this reformulation with the exact dual certificate, the so-called, what we call the putting proposition. And so now we find an exact dual certificate. And let me recall what this is. So we have that if we project on the tangent space, we are getting the true solution back. And if we're projecting to the orthogonal complement, then the spectral norm of what we get will have norm bounded by, here I'm just plugging in the constants, then we're getting 3/4. Okay. So the other thing that I'm recalling, which is something that, I mean, we have spelled out in the paper with Dominic, but I think it shouldn't come to surprise to those who have thought about this, that if we have and so like a vector z that is in the descent cone, that it needs to look like the following. So we have we should think of M is what we have. Oh, sorry. M is what is this is the part that's in the tangent space, and this is the part that's orthogonal to the tangent space. And the idea is that this part orthogonal to the tangent space, like in order to introduce some parts that are orthogonal to the tangent space and still reduce the nuclear norm, what we add here in nuclear norm must be smaller than what we subtract here, because otherwise the nuclear norm will increase. So that's why if this has nuclear norm beta, then this also must have nuclear norm at most beta. So that's the main idea. This is what you can show. I think it's fairly natural. These are things that are somewhat in the tangential directions. They don't have an impact on the nuclear norm, but this one reduces some part of the nuclear norm in the direction of the rank 1 solution that we started with, and whatever we reduce here, we can add later on and still have not increase the nuclear norm. So that's the intuition of this. So this is like just some recap, because we will be using this, and now we're putting things together, because the idea here is, like, recall that we want, okay, this is good that I'm having this here, because I'm just noted that I added what we need to estimate here in the is the, if you think about these conic singular values, I mean, we know that the conic singular values itself are bounded, but the numerator of the conic singular value is the 2 norm of the measurements of our element in the descent cone. And this is what we're now providing a lower bound for. So it looks like this. Here added 9/4, because what is the idea? How to get the lower bound to the 2 norm? We're taking the inner product with just some vector of norm 1, say, and in this case, this would be exactly this dual certificate that we had. So it's just, this is true for the 2 norm, like this is just Cauchy-Schwarz to bound this above by this quantity here on the left, because we know that this z has, this was an assumption that we had earlier from this putting proposition, that z has a norm bounded by 9/4. So when we're getting this inner product here, this is bounded from above by the quantity that we're looking at, up to this constant that I just added here, to not have to carry it around. Okay, now the idea is, now we have this A, and we can put it to the other side. And then now we have the dual certificates Now we have the element in the descent cone Z, and on the other side we have A star Z. A star Z, we know that's exactly what we called Y in the previous slide here. This is Y is A star Z. And now we can plug in Y here. And for this, we use what I just explained to you, the general representation for an element in the descent cone. And now we can use all the properties that we had from the exact dual certificate. The first thing is, let me recall what they were. The first thing is here, if we project on the tangent plane here, tangent space, then we're getting just HM star back. And so if we're looking at the inner product with these components that are all in the tangent space, these two things are orthogonal to HM star. So the inner product will only act on this one here. And so then we have HM star, inner product HM star, that will give us negative beta. And then for the part that's orthogonal to the tangent space, we just that's just this M here on the left-hand side, and on the right-hand side, this would be the projection of the orthogonal complement. And now we're having this inner product here, and we can split it up into the nuclear norm times the spectral norm. And this is exactly the two quantities that we had. The spectral norm, we had a bound from the assumption of the dual certificate that was bounded by 3/4. This was bounded by beta, and so everything together gives us something like negative 1/4 betas.
This norm being larger than something, and then you have to think less than something.
Okay, you are. Yes. So okay, yes, you're right. So let's just do it like this. Let's just turn it around and put a negative sign here. This is, yes, you're right. And then we have a negative sign in front of everything. And then, yes. Yes, we reverse the inequality, and then we have, yes, sorry, yes, thank you. This is correct. Yes, the idea is that this quantity this inner product here is negative, but we would need to put absolute values around, and so that's why the inequalities all go in the right direction. But you are right that this needs to be corrected. So the only thing is, the most important thing we get from this is that this number of measurements that we need to be lower bound, it can only be small when this quantity beta is small. So if we think of here, we're having an element in the descent cone that has norm 1. Let's look a little bit back on this formula. What does it mean? So beta is small. That means this part is small. We know that M also has nuclear norm less than beta, so this is also small. So this, if the norm is 1 and these two things are small, then this must be the large part. So these are the things that are really tangential and sort of, but not in the direction of the true solution. So here, either we're keeping one H fixed and then going tangential off in the other direction, and vice versa. So basically, this is the thing is, if we're thinking we are sidetracking in a tangential direction. That's sort of this idea. So we are very close to this this behavior. And then the idea, if we look back at the picture that I showed you, is that basically here in the picture, HM star would mean going down in the direction of the true solution. So what we're having here would have a very large potential that would go sideways. And as you can see here, because of the curvature, if you really go sideways, then you cannot go very far because things are curving. So in particular, what we could show is that if we have such an object here, we can only take a step on the order of beta, and then we will leave the descent set in such a direction here. And so that gives us this square root or quadratic scaling, depending on how you look at it, because we have one beta from here and one beta from how far we can go. And that's why we get this dependence, and that gives us our result. Yep. Is that somewhat clear? I mean, I think I don't have time now to go into the details. This is getting a little bit technical, the last part, but I hope that the idea, so this idea of sort of shuffling, like, I hope that the idea of combining the primal perspective with the descent cone and the dual perspective, and I mean, as it's natural, the dual objects are meant to take inner products with the primal object. So in some sense, this is like, looking back, this seems very natural to me. But I think and that's maybe an explanation why things work out so nicely, that you exactly get the right norms that match. And so just in the last 10 minutes, this was sort of what we get for blind deconvolution. Let me just quickly see, also show what we have for matrix completion. I mean, just a very quick recap here. I think you all know this, that this problem is motivated by many, like, for example, by the Netflix problems. The idea is complete a matrix of user ratings, and there is one ingredient. I mean, the solution that has been employed was of course a hybrid method that has many ingredients, but one of the things that has been proven useful is to use a rank prior that has also been mentioned. So here it's a picture that you have a matrix that has some values added and you want to complete the rest. So let's just put this into formulas. We are having a matrix of rank R, let's call this X naught. And now we are having a measurement operator that extracts the ith entry. And in order, again, we want to have, as I said, we are looking for something that has the restricted isometry property on the tangent space. So we need to have an appropriate normalization, and that is exactly this dimension divided by square root of number of measurements. This is due to the fact that, like, the number of the expectation of the measurement vector should be the same as the norm of the matrix in some sense. So that's why this is a natural normalization. And then we proceed just as before. We are looking at these types of measurements of our matrix and add noise. So algorithm is also very analogous to the previous situation. We are minimizing the nuclear norm subject to the L2 norm constraint. And this is a result that dates back even earlier to 2010 by Candice and Plan, that looked at these rank matrices. Okay, I think one slide here, the slides got flipped, sorry. So we have that the incoherence parameter is required, in the sense that, like, the reason here is also very natural. If you have this matrix that has just a 1 and otherwise zeros, and you sample random entries of this matrix, you will never find this 1. So this is very unlikely that you hit this 1. So it's very unlikely that you will properly complete this matrix here. So that's why we again need some incoherence parameter. They are now called mu of u and mu of v, that ensure that the mass is well distributed across columns and rows. I will not go into the details here. The only thing is that if we have such incoherence conditions, then we get a reconstruction, and the same way we get this dimension factor squared of n that shows up here, as we had in the blind deconvolution case. And as in the blind deconvolution case, we also have this negative results for some small noise levels. Namely, we have an alternative solution that is feasible, that is preferred to the truth in terms of nuclear norm minimization, and that is far from the true solution, the Frobenius norm, in the sense that in the scaling of the noise, there's the noise level happening plus some additional dimensional factor, which again, you can show in the scenarios that you're interested in has this scaling of square root of n that we had in the previous result. So this is very much analogous in the sense that it's somehow necessary in what sense. And now we are trying to do the same thing. We are having the same assumptions here. And now we are looking at the solution of the constrained nuclear norm minimization problem. And then what we get is, again, we have two regimes, square root tau regime and the tau regime. But for this square root of tau regimes, we get still a factor of r to the 1/4. Like why 1/4? The idea is that I think it is under the square root. It would be another square root r factor, which is somehow natural, because in one way, what we're thinking and we're trying to work is if this is actually the nuclear norm of x0 that happens here, because that would sort of be an explanation why you have the square root. And I think this, but we're not there yet. So this is something that we expect may be the case. But so in particular, we're getting again something that sort of bridges the zero approximation error at 0. I think that even if we have this r to the 1/4 factor, this is it's fairly nicely behaved, because the rank of these, and we're looking at low rank matrix recovery problems, the ranks are assumed to be much smaller than the dimension. So having such a factor is much less of an obstacle than a dimensional factor. And we can again get these two regimes. So as I said, we're still working. We're hoping that we're getting to the nuclear norm, which would be slightly stronger even here, but that's something that's still work in progress. The outlook and open questions. So first of all, what can we say about the actual minimizer in the scenario of small noise? Because we said that we know that there's an alternative solution, and I think that's basically how all these how all these proofs works, because we would say basically all alternative solutions would either have a larger nuclear norm or would be very close to the true solution. So this is not the case. It's nevertheless, if there's multiple alternative solutions, like looking at the true minimizer, it seems much more difficult, and it would be very interesting to see if this true minimizer actually is close to the true solution or not. We have been trying to, we've been going back and forth, trying to either show that there's a counterexample or that it's actually the case. We just don't know. The other thing is we have this rank factor in the last result that I show you, r to the 1/4. And my feeling is somehow that if you think about what you can do with adversarial noise, you can put noise only in one single entry somehow of your measurements. And I assume that with these examples, that would never happen with random noise. You would get some additional rank factors or factors of that type that are unavoidable, but the question is really what is necessary and what can be done. And that's something that we're working on. And then there's some scenarios that were also considered in this context in the literature, blind mixing and deconvolution, where you have, like I showed you, one sender is sending a message through one channel and then there's one receiver. But that's not typically what happens, because there's typically multiple senders that are sending messages at the same time. So you're observing a superposition of these different convolutions. And that's a problem where this original setup has been analyzed, but not what we weren't able to cover yet in our analysis. And then, of course, what I haven't listed here, so the very important open question, so what happens to non-convex algorithms? So because this is, I mean, the benchmark, I think, you know, as I said, the literature that I cited was a few years ago. A lot of understanding has been gained for non-convex algorithms that are more efficient. You have heard Christian's talk, for example, and others. And so you would probably not use these algorithms here, but for these non-convex algorithms, a lot less even is known on what happens for adversarial noise or for these different noise models. So, and that's why we also see this sort of as a starting point for an analysis of that type. So but these are all open questions for the future. So if you have any comments, if you're interested, I we're currently working on the preprint, so this is the last part is not out yet, but if you have any questions, I'm of course happy to tell you a little bit more if you're interested.